who is coming to us from Bern, and she's going to be speaking about symmetries and stuff will give in string theory.
Hello. Let me first start by thanking the organizers, Miriam Johnson and everyone else who helped put together this very nice conference. And also for inviting me and giving me the opportunity to join you online, even though I couldn't be there in person. But in any case, I watched all the talks online, I enjoyed them, and I hope to see you next year in Hamburg. Okay, so I'm going to talk about symmetries and how they can be realized in string theory and how we can classify them in a string theory. This is based on work done together with Fabio, Federico Iñaki, and Sakura a while ago, and also work that's to appear with Iñaki. Okay, so as we heard in many talks before, when we have a quantum field theory, in order to specify it, we need to know what its spectrum of, not only what spectrum of the local operators are, but also what spectrum of higher dimensional operators we have. These higher dimensional operators, they're associated to symmetries. And so if we have quantum field theories which have the same local dynamics, they may have different extended operators and so different symmetries and global structures. And this was explained in details by a lot of talks by Monica, Ibu, Iñaki, and also just today by Sakura. So in one way to go about and understand this classification of these different global structures is to take our quantum field theory and realize it as a boundary theory of a bulk BF theory. So this bulk BFT theory, it can have different boundary conditions, and different boundary conditions, they correspond to different choices of symmetries that this boundary theory can realize. And in this talk, I would like to tell you how we can obtain this BF theory from a dimensional reduction of the torsional sector of string theory or M theory by looking at self-dual fields there. Okay, so as we saw in a lot of talks before, we have this picture where we have this topological field theory in the middle. This is now BF theory. It has an action of the form K B wedge dA, and it's defined on this manifold N, which is D plus 1 dimensional. And here we also have on the right-hand side, the boundary theory, tau, which is D-dimensional. Now, if this BF theory in K here is not 1, then the Hilbert space of this theory would have dimension greater than 1, which means this is a non-invertible theory. So we could have different boundary theories on the right. And these gauge fields here in this theory, they can have different boundary conditions. So they can end on the boundary or not end the boundary, as we just saw today and before. So, and if they don't end on the boundary, then we get symmetry operators. And if they do end on the boundary, we get defects. So depending on which one of these we choose to end or not, we get different types of symmetries, symmetry operators, and so symmetries. So once we fix the boundary condition on the left, which is on this ID, then we collapse this yellow bit, and then we get an absolute theory on the right-hand side. Now, more generally, we could have anomalies. So for these symmetries, and what happens is that the picture gets modified. Here we would have on the left-hand side, we would have an invertible anomaly theory, and then once we fix the boundary conditions on an ID, then we end up with this absolute theory on the right-hand side and with its anomaly theory. Now, in general, we would like this symmetry TFT not to only tell us about the classification of higher form symmetries, which I was just mentioning, but also more general categorical symmetries and their anomalies, as we heard by Sakura and others. And so there is some progress done in this direction to understand this from string theory, and we heard a lot of talks on this before. Okay, so how do we get this BF theory from a string theory? Well, we saw in the talks before that we can get it from this non-commutativity, but I'd like to tell you about a different approach. So if we start with string theory or M theory, when we put it on this product manifold, CL times MD, we can, by geometric engineering, reduce on CL and get a field theory on MD. So here CL is a Calabi-Yau, it's singular, and it can be realized as a cone over this base L. Now, this data of geometric engineering, this does not quite tell us what the possible symmetries are in this field theory that we obtained. What we need to construct is this symmetry TFT, topological field theory. So this is the same picture again. We put string theory on this cone times MD, we get a field theory on MD. Now, in this paper, we said that we could instead put string theory, which is based on these previous works, could put M theory or string theory on this base L and extend this N M, where we have the field theory, to N, and then reduce on L. In this case, we find exactly D plus one-dimensional theory, which is the symmetry TFT. Now, this is again, same thing, we reduce on L, we get a D plus one-dimensional theory. And how does this work in equations? So mathematically, we looked at this Chern-Simons topological action in M theory. We reduced it on L, and then we found some action on D plus one, which tells us about the anomalies in SymTFT. Now, one thing we weren't quite sure how to do is to get the BF theory from a reduction of an action. And so we want to answer in this talk, what is this action that we need to reduce in order to see this BF theory. So to answer this question, let us go back to the origin of the BF theory. So as Niaki discussed in great details, these supergravity fluxes do not commute. So if you're in M theory, we have F4 and F7 fields. The fluxes for these fields, they have this non-commutativity relation. And here L is the linking on the asymptotic boundary of where this supergravity lives, and these F4 and F7 are convergent classes, so they link. And we get these symmetry operators from reduction of these fluxes. So if these fluxes don't commute, this means the symmetry operators are not going to commute, then we reduce. So if this BF theory was to come from an action, it would be an action that involves F4 and F7. And the closest object that we know in string theory, for example, in M theory, is this F4 with a star F4, knowing that a star F4 is F7, ignoring the other terms for now. However, the reduction of this action does not quite work. It doesn't give us what we want if you're not careful. So what we have to do is to go construct a Chern-Simons action in one dimension higher, which realizes these self-dual fields as boundary modes. And this was discussed, for example, by Witten when he was discussing M5 brane action, or in these some papers by Blove and Moore, where they discuss type 2 actions in terms of the Chern-Simons. And here in M theory, we have not a self-dual field, but a self-dual pair. And this was also discussed in this paper by Fried. So what we want to do is to define this 12-dimensional Chern-Simons theory in one dimension higher. So in M theory, what we would do is we extend this manifold ND plus 1, which was where our BF theory or symmetry TFT was defined, to one dimension higher. So we defined the D plus 2 so that it has boundary N. And now we put our Chern-Simons theory on this manifold L times the D plus 2. Then we reduce on L, and then we get a theory on D plus 2 dimensions into D plus 2 dimensions. And then if we use a Stokes law, we could go to ND plus 1 and get the BF theory. We will see. Okay, so now you may, so what's really important is that the reason that we get the non-trivial BF theory or symmetry TFT is that this manifold that we are looking at, this L, specifically, it has torsion cycles. And so we have to be careful when we construct this action. We need to consider fields to be topologically non-trivial. So let's go and construct a Chern-Simons that takes that into account. Okay, so we have all seen this abelian Chern-Simons theory at level K. It has an action of the form K integral over M3 of A wedge dA. Now, gauge invariance tells us that this level k has to be an integer. However, if we introduce a spinor structure, then we have that this means that nu2, the second book class, should trivialize, and this means the following. So we can extend M3 to one higher dimension to M4, and we write this A wedge dA as dA wedge dA using a Flux theorem. Then we can map this A, which is a form, to a cochain using the Ram's theorem, and to rewrite this as a cup product. And this is A is one-dimensional, so this would be two-dimensional, and this is cup product of two middle-dimensional classes on M4, which means that it can be rewritten in terms of the product of the same class with the second Boole structure, but we chose to have a spinor structure, so this nu2 vanishes, and this is 0 mod 2. So we know cup product on spin manifold is even. So therefore, we can now divide our Chern-Simons that we had before by 2, and this would make sense. And this is important, we want to divide by 2 because when we think about boundary modes, when we realize this self-dual fields as boundary modes, we want to count the right degree, the right number of degrees of freedom. And so this is important. Okay, now let's go back, see how we can get these not an action for topologically non-trivial fields. So let's say we have a p-1 form gauge field. Then in order to specify it, we need the following data. We need the curvature f, which is a closed form of degree p. We need the characteristic class. This is of degree p also, but it lives in singular or integral cohomology with integer coefficients. And there's also a connection associated to this, which in general is a cochain of degree p-1 with coefficients in R. This formulation was done in Hopkins and Singer, and there is a different version earlier done by Saghar-Simons. So we represent such a gauge field by this funny A with a hat on it, and it has three components: the characteristic class, connection, and the curvature. And since F is closed and N is a class, we have that D of them is 0, and dA in general would be F minus N. So unless we have that this gauge field is topologically trivial, so that N is 0, we cannot globally define F to be dA as we usually do. That would be only locally but defined. Okay, so now to define the Chern-Simons, we remember that we have two A's in the Chern-Simons, it was A, dA. So we need to define the product of gauge fields in this notation. So say we have two gauge fields A and B, then their product would be as the following. So the characteristic class of the product would be the characteristic class of the A times the characteristic class of B. The curvature of the product would be the curvature of A with curvature of B. But the connection part is a little more complicated. So here the curvature, the connection of the AB is the characteristic class of A cup the connection of B plus the connection of A times curvature of B plus H, this H of F and B, F of A and B. And this H, so we know that by the Ram's theorem that there's isomorphism from differential forms to cochains. And so the cup product and wedge product are homotopy equivalent. So their difference can be defined by this map H, by this homotopy map, which is a cochain. So here we have W and W prime, they are forms. We find their wedge product, we map two cochains. And then here we have W, which is a form, we map it to a cochain, and similarly with W prime, it is a form, we map it to a cochain, and then find the product, and then the difference would be defined by this map. Okay, now that we know how to find the product of these gauge fields, what we need to do is go on and define our Chern-Simons. So here we define the Chern-Simons to be the product of A and A times K over 2 integrated over this M2. So remember, so here we are looking at a one-form gauge field. So it would have a curvature and a characteristic class which would have degree 2. So if you were to multiply the characteristic class of A itself, you would find a form that's of degree 4. And for the curvature also would be of degree 4. So we would that would vanish if we were to integrate over M3. So the only non-trivial part would be the connection part, which has this form. So now we see this is the Chern-Simons that we want. As before, here we have the factor of 2. So we want to have a spinor structure, and doing similar kind of argument, we could see that this is well defined because this couldn't be even. But what about more generally? What if we move to higher dimensions? And what if the dimension of M is 4p minus 1, 4p greater than 1? So here, in this case, we can do the similar thing as before. We extend M to N. And so we go to one higher dimension. And for simplicity, we can take A to be flat. Then extending M to N, we can rewrite this product as the characteristic class of N cup itself. But we know in general that an arbitrary 4p dimensional manifold and the cup product may not be even. So what are we gonna do? So, but what we know is that if we have a middle dimensional class, homology class of degree 2p and a 4p manifold, then the cup product of that with itself would be the cup product of the same form with class with the second, not the 2p Wu class and mod 2. So if we take the difference of these two, which is this thing here, we would find something that's 0 mod 2. So in other words, it's an even integer. So then the division by 2 makes sense if we were to define the Chern-Simons like this. Now, more generally, we don't want to define the Chern-Simons on N. We want to stay on M. And so what we can do, we can define this lambda, which is defined as follows. So here it has the characteristic class N, but this is equal to the Wu class of the same degree mod 2. So but it also has this connection and curvature. So if we were to take this definition, then we could all still divide by 2, and this would be a good Chern-Simons. Okay, now we want to, so before, remember, we didn't have this lambda in 3 dimensions because we chose to have a spinor structure, and we could just, this would trivialize this new 2 that we would have here, or the differential version from. So we want to generalize the spinor structure to higher dimensions. And this is what's called the Wu structure. So remember, a spinor structure can be realized as a trivialization of a degree 2 Wu class, which on an orientable manifold is same as a second Stiefel-Widnig class. Now, a degree 2p Wu structure can be realized as a trivialization of a degree 2p Wu class, which can be also written in terms of Stiefel-Widnig classes. So for example, if we have an 11-dimensional manifold, then, and if it's orientable, we define this Wu structure to be the trivialization of a degree 6 Wu class, which can be written in terms of W2, W4, and W3. Now, if you have a Wu structure, then we can just define the Chern-Simons to be this K over 2, A times A. Okay, now the whole point was that we wanted to construct this Chern-Simons to define, to realize this self-dual phase as boundary mod. So how do we see that from this Chern-Simons? Okay, so let's just consider a simpler example where we have a Coriolis scalar in 2 dimensions. Then this is a Chern-Simons that we want to see this Coriolis scalar as its boundary mod. But in order to see this boundary mod, what we need is to add this kinetic action for this gauge field A, which has the form 1/2 of E squared, the curvature of F times star of curvature of F. Now, if we substitute for A times A, the connection that we define the product, and find the equation of motion, we get 1/2 of E squared times D star of F minus IF is 0. Then, in order to see the boundary mod, we want to choose the boundary condition where A vanishes, the 3 component of A vanish on the boundary of M. So boundary of M3, I call it X2, which is where the color is gathered. So if we take M3 near the boundary to have the following form, it would be an interval from minus epsilon to 0 times X2, where at 0 we have the boundary X2, then we can take our F to have the following form. So it would be DEM to the tau times FA, where tau here is the coordinate on this interval. And FA is a form defined on X2. So then if we substitute this F into this equation of motion, what we find is that star of A is IF and D star of FA is 0. And these are precisely the equations of motion for self-dual fields FA living on this boundary X2. So very good. We have this. We see that this is our boundary mode. Now, how do we see the how do we get the BF theory? So to see this, let's go and look at some examples. Okay, so in type 2b, here we have a four-form RR field, which is self-dual. It has connection C4, characteristic class M5 at arbitrary of 5. This can be realized as a boundary mode of this Chern-Simons defined in 11 dimensions for this gauge field G6 with these components. So how do we get the BF theory? Let's look at an example. Michele mentioned this example. So we would type 2b on C2 mod Zn times M6, we get 62,0 theory. Then what we need to do is to find, so here the symmetry TFT would have dimension 7 corresponding to this 60 theory. So we want to define an 11, we take it to be the base of this cone, which is S3 mod Zn, times Z8, where ZA is the extension of this N7, where this N7 is where we define our symmetry TFT. So we extend N7 to Z8 and we put this Chern-Simons on this 11-dimensional manifold. Then if we integrate this Chern-Simons over this S3 mod Zn, we reduce it on S3 mod Zn, we find an 8-dimensional integral. So then C4 is a differential form on Z8. Then if we assume that H4 of this C4 is 0 on N7, then C4 trivializes on N7 to C3, and we can rewrite this using a Stokes theorem as an over 2 integral of N7 C3 with d C3. And this is precisely the BF theory corresponding to the 62,0 theory, or the Chern-Simons theory. Now you may ask, okay, does this action, this Chern-Simons, classify all the possible 62,0 theories, and can we always make them absolute? The answer is no, not in general. So that it is only in some cases where we can impose consistent boundary conditions to make this 60 theory absolute, and this was discussed here. Namely, when n is a whole square, then we can have a relative 62,0 theory. Okay, now let's move on to M theory. Here we have a not a self-dual field, but a pair of self-dual fields, F4 and F7, which can be realized as boundary modes of this Chern-Simons theory, G5 and G8 over N12. Now, okay, we would have half, but 2 of these, so they would add up to cancel the half. Okay, so let's look at another example again, where we put M theory on C2 mod Zn and times M7, and we reduce it on C2 mod Zn, then we get 7D n equal 1 theory. And this theory would have an 8-dimensional symmetry TFT. So we again extend this 8-dimensional space to Z9 and put this Chern-Simons on N12, which is S3 mod Zn times Z9. In this case, again, we can make some assumptions, specifically where we assume that H3 and H6 of N7 vanish, and then we can trivialize this C3 and C6 to C2 and C5 on N7. And then we can rewrite this action on this 7-dimensional manifold, which is again precisely the BF theory we expect to find for this 7D n equal to 1 theory. Now, this brings me to my conclusion. So, as we saw, we can construct a BF action from a reduction of Chern-Simons action for self-dual fields in a string theory by taking into account the torsional effects. And the ultimate goal would be to classify not only these symmetries, high form symmetries, but also more general categorical symmetries like non-invertible symmetries, which we heard about, and their anomalies. So there has been a lot of progress, as we heard, in this direction to get these from a string theory or M theory and so on. But there remains to be much work to do to complete this picture from this perspective. Finally, maybe a direction to go is to see what the reduction of these defects that we heard about earlier in these talks that are realized by this cobordism conjecture, and what happens when we reduce those on manifold with boundaries, and what role they play in symmetry TFT. Thank you for listening.
Thank you for the talk, Sophie. Questions? Yes.
This is the presumed so which might studies
Sorry, I can't hear you very well. If you're asking a question.
Hi, thanks for the nice talk. So I was wondering, so to preserve supersymmetry, does that pick out for you a canonical Wu structure in a lot of these cases?
Can you go? Sorry, what? Missed it.
So,
Sorry,
so the question is,
yeah.
in, for example, a lot of times preserving supersymmetry picks out a canonical choice of spin structure at the boundary. Is there a similar statement of a canonical choice of Wu structure to preserve supersymmetry?
So yeah, so when we reduce on this product manifold, this Wu structure automatically induces a Wu structure or spinor structure depending on the lower dimensional space. So yeah, that is the case. We have this, so we know that the product, we know if you have a Wu, like a Wu class, then we can reduce this to product of Wu classes, and we'll see that that happens. Yes.
So I was a little confused by something. You were constructing this pairing on the self-dual fields in, say, type 2 string theory in sort of differential Eilenberg-MacLane cohomology, but at least a weak coupling, we know those fields are valued in differential K theory, and rationally those are the same, but the torsion is completely different. And so that I'm a little confused by.
Yeah, so that's exactly right. So this example, so in general, of course, this we have to be careful. But I was more interested to look at examples that I know the higher force symmetries of, like this is space where we can use that, look at the spectral sequences, then differential cohomology classes reduced to differential K-theory classes reduced to differential cohomology classes. But in general, we should go back and construct this in K-theory really. Where, like in papers by Blau and Moore, they studied this K-theory construction of Chern-Simons action for type 2. And yeah, if we should start from that, then maybe we could find some more interesting results in more general manifolds. Because here I'm taking M6 to have no torsion, and that lets us reduce this to just differential cohomology. Thank you for that.
Thank you. So we can do time as well.
One question I have is, in M theory, you also have the Chern-Simons term, right? And you in principle would also on top of this basically quadratic refinement, you would have a cubic refinement. Can you say something about that, or does it appear naturally also when you include it in your discussion?
So I am not exactly sure what is this other term you're talking about. Maybe is this where we have the gravitational anomalies in the quadratic refinement?
G4, wedge G4, right? You could also include it in your 11-dimensional manifold, and then you would lift it to G4, cup G4, cup G4.
Oh, okay, yeah, exactly. Yeah, there is that term too, and so I didn't look at it from this perspective here. Didn't include it in this discussion, but that we did. That is what we really discussed in this paper. So in this paper, what we did, we reduced this term where we would have G4 cubed if we go to differential cohomology, and from reduction of this we find anomalies. But in the context of Chern-Simons, well, we need to modify the discussion. I mean, we need to change this discussion to lift to this higher dimensional theory somehow to encode this extra term.
Thank you. And can I have another
Yes.
quick question? So at some point you took a differential lift of your Wu structure. So
Yeah.
I wondered whether it has a physical implication of what kind of lift you choose. So of course this is not, so you could just take different choices, right? This would probably induce some like background coupling of your gauge fields to some classes. And I was wondering whether it has a physical meaning.
Mm-hmm. So I'm not sure of a good answer for this in general, but for example, if we are in 11 dimension, then if you impose the spinor structure, we automatically get this Wu structure. And yeah, I'm not sure if that'll be or in this what implications there would be physically. Sorry. Thank you for the question.
Yeah, thank you very much for the talk. Let's thank Sophie again.
Thank you for your attention.